Okay, this part is about a mixture of experts, and I know that sometimes it doesn't necessarily, so Mistral doesn't necessarily have mixture of expert, but Mistral definitely has that part. But the thing is, according to code in Mistral, if you go and have a look, we can just do it quickly here. So if we have a look at transformers layers, we can see that in this block, I think it should be right here. Yeah, in the feed forward part, as you can see, we have a kind of MoE checker, which checks if we want this feed forward layer to be a simple, in fact, feed forward, or a mixture of expert layers. So that's why I'm gonna cover a mixture of experts here in Mistral. So what it says, according to this diagram, as you can see here, just imagine that we have transformers, vanilla transformers, and mixture of experts. What happens, everything is the same in input and encoding. Let's say the decoder block, layer norm, mask self-attention, and again another layer norm. But what happens is exactly in this part. So in transformers, what we have after all those calculations, all those will be given to a feed-forward network, and this feed-forward network will, it could be, I don't know, classifier or whatever that it is, it will make some decision and it will output whatever the output is into the decoder block. And it is just simply a very big, giant feed-forward network, which has lots of parameters. But the thing is, imagine that you're in the inference time, and this network is too big. Why you should do inference each time on such a big network to make some decisions? What you can do, maybe, instead of a very giant network, have a couple of smaller networks, just like here in mixture of experts, which each of them are expert in a specific field. And imagine that you have another small feed-forward network or another logic, which we call it router or gate, which can decide which of these experts need to take care of that incoming token. So imagine it in this way. Imagine that, I don't know, you want to talk about something, or the input token is about, let's say, any topic. You can give it to a very big network, which is expert in all the fields, but it has lots of parameters. But the other thing that you can do in mixture of expert is, alternatively, you can do this. Take a look at that input token and decide which of these experts are the best to handle and deal with that incoming token. So what's the benefit? The benefit is you don't need to activate all these experts on inference time. You can, let's say, you can specify top k, let's say top k equal 2, and you can say, okay, just 2 experts look at that incoming token. So the thing is, you have the same strength in the model because you have lots of experts. It's the same as this giant feed-forward, but you don't need to use all of them, which means you are much more optimized, and you don't need to, you don't need to burn lots of GPUs for that. So yeah, briefly explaining, so mixture of expert is just a type of neural network architecture that is dynamically, this is important, routes input data through only subset of specialized modules. We can call them experts. It's just inspired from humans that they delegate tasks to each other. And yeah, I explained about these gate and top case, so on and so forth. But about the analogy, and you can, this is a good analogy, I would say. Just imagine that when someone is, I don't know, sick or whatever, imagine that the guy goes to hospital, and hospital has lots of doctors. You can't go and talk to each of them. So what you do is you literally go to receptionist and talk about, you explain about your problem, and receptionist, which is gate here, just routes you through the best doctors. So yeah, that's how it works. And also it's worth mentioning that the top K experts can tell us that our version of the mixture of expert is sparse. If top K is, for example, the K is 2 or 3 or 1, or if we use all of the experts, that would be dense mixture of experts, or sometimes I think they call it soft mixture of experts as well. So a very simple example of that would be something like this. It's very simple, not neural networky. It is just imagine that we have 3 experts and these are returning, let's say, imagine if it is the input is x, it returns x plus 1, expert 2, x times 2, x to the power of 2 is the third expert, and the gate would be something very rule based, and if x is less than 2, do something, if it is less than 5, do something else, just do something else. So this is technically the logic behind it. Very hard coded. But about a more advanced example, I can say a sparse mixture of experts with top K gates. Imagine that we have 3 expert neural nets and we want to do a top 2 experts. So what we have here is we have the expert initialization, the expert class, which is just simply a linear layer, or just simply a feed forward with input size and the output size dimension. The feed forward is just literally just giving the tensor into that expert. The gates are just the input size, and the output size is number of experts, because we want to see that in that tensor we want to have the logits and or softmax to decide which agents we need to choose and which agents we need to route the input further on. So we initialize the sparse mixture of experts. We have the experts themselves, the top K, in fact the layers of the experts, and initializing the gates. So what happens technically here is we just simply give the inputs to the gate, and then gates decides that, okay, based on that top K, because gate is a learning neural net, feed forward net. So the gate decides that, okay, what are the top K guys or experts who can, I don't know, fix this problem or deal with this token, input token. It will just give us the indices and we can do the softmax, and I will tell you why we do logits and softmax as well. And once we have all those experts, we can route and give the input token to those experts, and then based on the weight that we have from the softmax for each of those experts, we can weight their output. Imagine it's just the same as saying that, okay, you have 3 doctors and one of them is really specialized the best. So whenever you have, I don't know, for example, you have a headache, when the best doctor tries to diagnose that, you give more weight to what he says to you and less weight to the 2 others. This is exactly what happens, and why we have these softmax weights. Once we give the input token to, let's say, 2 experts, we give also the weight to their decision, and then we calculate whatever the output is. So yes, this is technically that's why we're using logits as well as the softmax. So we use them because we want to weight the decision of the experts, in short. And also the other question is, I don't know, if each token is processed by its own expert or a few experts, how the hell they know what's the context of the full sentence? So the thing is, once we give the input to the experts, they have already passed from the self-attention, so they do have information of the whole context and sentence, so there is no need to worry about anything like that. Just a quick look at mixture of experts code, which is derived from Mistral GitHub repo. I just add more comments and explanation to easy understand that, and I will put it into my GitHub repo so you can have a look at it if you like to learn more. So what it does, we have a bunch of inputs, imports, and then we have a MoE Arcs, which is a data class, and it simply defines, has the number of expert as integer and the number of experts who will be given to each token. So how many experts need to make decision about each token. So technically this is the same as top K. And then here in the MoE, a mixture of expert layer. So what we have simply, this is just the same as what we saw in the previous code. We have a number of experts, which is just a module list and full of experts, which could be neural nets, and so on and so forth. And we have the gate, which is also another neural net, which decides to which experts route the token to, and the arguments. And simply what we do here is just we initialize the gate and we give the input and we get the logits. Then we do the top K based on the number of, in fact, top K or number of experts per token, which we defined in this data class right up here. And then again, because we want to weight the decision of each of the experts, we do a softmax and we put them into a, let's say, list or tensor, whatever that it is. And then in this for loop, what we do is technically, now we have the experts. We give the input to those experts. They will tell us about their decisions, and then we multiply those decisions to the weights derived from this softmax weight, and then we have all the results. Yeah, so this is technically how the mixture of experts works. And as I mentioned, if you go to GitHub of Mistral, you can see that in the, so this is the file which is called transformer layers. They have something called feed forward, self.feed forward, and they decide, you can decide that whether this feed forward could be or should be simply a simple feed forward with LoRa, which we will talk about next, or we can decide it to be mixture of expert layers. And yes, that's it for mixture of expert part.